Hello everyone, you're watching the Space Channel. Today we're going to talk about multiverses. You've probably heard of this idea only in the context of science fiction films and books, where the heroes travel between worlds that exist in parallel. These universes can be almost identical or radically different in the flow of time, the structure of space, and the laws of physics. Somewhere in these worlds, the heroes may even find their own doubles, beings who look the same on the outside or who share a combined consciousness. So far, all of this sounds beautiful but detached from reality. Yet the hypothesis that we live in only one of the worlds of a multiverse might actually be the tool that lets us resolve the fundamental contradictions in modern physics. In the end, accepting the existence of multiverses as an objective fact could help scientists finally create a physical theory of everything. To see how this might happen, we need to look at the starting point of the universe we live in, the moment of the Big Bang. Today, the Big Bang Theory stands at the forefront of our cosmological understanding. It says that more than 13 billion years ago, out of nothing and absolute emptiness, a tiny speck emerged, which suddenly exploded and expanded into the cosmos we know. The first scientist to give us a theoretical framework for explaining what might have happened at the moment of the Big Bang was the remarkable physicist Albert Einstein. In fact, he provided the scientific community with approaches to this problem from two angles. In 1905, in his scientific papers, he laid out the justification for the theory of relativity and introduced the concept of the smallest elementary particle, the quantum. The theory of relativity became the starting point for exploring the nature of gravitational interaction on the gigantic scale of the cosmos. At the same time, the concept of a quantum was key to founding a new branch of physics devoted to the tiniest elementary particles, quantum mechanics. Both the theory of relativity and quantum mechanics became revolutionary physical concepts that solved many unsolved questions that had accumulated over centuries. However, these concepts created a new major problem. They are incompatible with each other. No matter how hard scientists tried, no matter how clever the mathematics, theories of relativity and quantum mechanics fell into a chasm whenever a physical process considered by both theories crossed the Planck scale. The Planck scale is the smallest size of physical quantities in our universe. That makes sense. These minuscule values are hard to imagine. But the key point is this. Any process larger than the Planck scale obeys the generally accepted laws of physics, including relativity. But if something is smaller than that scale, it lies beyond the control of those laws and can be described only by quantum mechanics. One example of something potentially smaller than the Planck scale is the hypothetical structure of quarks. The critical incompatibility between relativity and quantum mechanics lies in their treatment of time. In relativity, time and space are relative and united in a single fabric, yet objects placed on that fabric appear separate and clearly defined to an outside observer. In quantum mechanics, by contrast, time is separate and absolute. It is used to fix observations, while objects of our reality are represented by wave functions that collapse and materialize into one of the billions of possible states at the moment of observation. As mentioned above, when a physical process crosses the Planck scale, it generates an insoluble conflict between relativity and quantum mechanics. At this point, we return to the Big Bang Theory because it was precisely due to this event that our universe grew, from a tiny particle smaller than the Planck scale into a vast cosmic expanse. From what we have just described, it becomes clear that relativity cannot be used to explain the processes inside our universe when it is as small as an elementary particle. At that scale, quantum mechanics should function. But things are not simple there either. Besides the incompatible perceptions of time in the two theories, another problem arises. According to the laws of quantum physics, even in absolutely empty space, certain quantum fluctuations occur that serve as a source of energy. This isn't critical so long as the universe is the size of a tiny particle. But the moment it crosses the Planck scale during the Big Bang, relativity kicks in. Its key equation asserts that energy equals mass. Therefore, In what is still empty space that is expanding during the explosion, an infinite amount of energy from quantum fluctuations would accumulate, turning into infinite mass. Where infinite mass arises, a black hole should form. Thus, by the laws of physics, our universe, right after its birth, ought to have collapsed into a black hole singularity because of the extreme concentration of energy mass. Yet that did not happen, nor did instant annihilation of matter with antimatter occur. In our universe, matter vastly predominates. All processes unfolded as though the excess mass, energy, and antimatter particles immediately after the Big Bang had somewhere to escape. But where? They could have gone to other universes. This is how a fictional plot device becomes a hypothesis that could potentially explain why we see our world the way it is. According to multiverse theory, our cosmos did not arise from emptiness, but inside a higher-order multidimensional space with which it interacts, albeit in a limited way. If the multiverse and the universes within it are real phenomena, what properties do they possess? Perhaps the best exploration of this question was done by Swedish-American physicist Max Tegmark. His first important contribution was the postulate that any set of physical laws containing no mathematical contradictions corresponds to an independent yet actually existing universe. Although this hypothesis cannot currently be tested experimentally, it is attractive in that it explains how the physical laws and the values of fundamental constants we observe are exactly the ones we've been able to confirm. His other significant work is a classification that contains 4 levels of multiverses. The first level of the multiverse is considered the simplest and most obvious. We find ourselves inside a kind of sphere of the observable cosmos. Its boundaries are set by how far we can see, that is, by the speed of light and the rate of the universe's expansion. If, beyond this horizon of our observation sphere, the same kind of universe with identical physical laws simply continues, then there are probably other similar regions out there. For example, if another observer is located 100 billion light-years away, that observer will see a completely different section of the universe, limited by their own sphere of observation. Although we are all part of one continuous space, the distances are so gigantic that we can rarely make contact. It turns out to look as if these are separate universes, just extremely distant ones. The second level of the multiverse is tied to the early inflationary period, one of the key elements of any modern cosmological model. The essence of inflation is that in the first fractions of a second after the Big Bang, the universe expanded incredibly fast. This stage lasted from 10 to the power of -36 to 10 to the power of -32 seconds. Yet during that time, the fabric of space grew by an unimaginable factor. Afterward, the expansion slowed, but it did not stop. For the second-level multiverse, it is assumed that inflation never actually ended. It continues constantly, but within a higher-order multidimensional space. However, in certain regions, inflation can randomly slow down and separate bubbles form, lower-level universes similar to our own. There can be infinitely many such bubbles, each with its own initial conditions, physical laws, and even different numbers of dimensions. Our universe happens to have conditions favorable for life to arise, but there could be bubbles where its emergence is impossible. All the separate universes exist against the backdrop of a vast field of ongoing eternal inflation. The third level of the multiverse already tests the human brain's capacity for abstraction because it involves applying quantum mechanical effects on a cosmic scale. Yet the point is not to apply quantum physics to objects that have crossed the Planck scale, but rather to the idea that observing or measuring an object can trigger the birth of a new universe. How might this happen? The key feature of quantum mechanics is the principle of superposition. A quantum object can be in all possible states simultaneously until at some moment we measure it. That is why in quantum mechanics, particles such as electrons do not exist as isolated points, but as a cloud smeared through space, the configuration of which is described mathematically by a wave function formula. The principle of superposition is illustrated most vividly by two famous thought experiments. The well-known Schrödinger's cat and the coin that after landing is simultaneously heads and tails until an observer looks and sees one side with a certain probability. Scientifically, after measurement, the quantum wave function that contains the probabilities of an object being in certain states collapses, and the observer sees the object not as a cloud, but as a distinct, separate image fixed at a particular instant. But what if we imagine that measurement is not the end of a quantum object's uncertainty, but merely a crossing point where past alternatives converge and from which future alternatives diverge? This astonishing idea is exactly what the third-level multiverse proposes. Observations and measurements of quantum objects give rise to new universes, whose number is not infinite, yet is so vast that it is hard to keep count. Interestingly, scientists still lack clear criteria for which particular observation of which object in quantum mechanics can lead to the birth of new universes. Thus, each everyday choice you make, such as deciding whether to order sushi or pizza for dinner, will not create a new universe. However, every time you observe a quantum system or use a quantum random number generator for trivial decisions, new universes really can be born. Moreover, they will exist in parallel and may have different laws and conditions. And in one of those universes, a copy of you will live. Yet with extremely high probability, you will never meet that copy. As for where the entire kaleidoscope of universes listed above might exist, we are talking about an abstract mathematical Hilbert space with an infinite number of dimensions. The fourth and final level of the multiverse is the most mysterious and radical. Here we speak of universes that not only exist somewhere else, but may have completely different physical laws. These realities are not necessarily located within our space and time, and might operate by an entirely different logic, built on different mathematical structures. For example, they might lack quantum mechanics altogether, or function according to totally different causal principles. In such universes, time might proceed in jumps, or might not exist at all. The fourth level does more than offer other worlds. It calls into question the very essence of physical reality as we understand it. Having familiarized ourselves with this multiverse classification, we arrive at the question of which proposed level could solve the following practical problem. Where did the excess matter and energy go after the Big Bang, allowing our universe to avoid annihilation or collapsing into a black hole singularity immediately after birth? The first level drops out because it offers only a single universe, albeit a huge one beyond our observational reach. The fourth level is excluded because at our current scientific stage, it is fundamentally impossible to grasp something lying beyond human logic and imagination. That leaves the second and third levels. The second level could theoretically solve the problem of migrating excess matter and energy out of the bubble of our universe. Yet today, scientists lack the mathematical apparatus to describe this process with sufficient justification. Surprisingly, though, researchers did find themselves ready to describe the mechanism for a multiplicity of cosmic spaces at the third level of the multiverse because, in the 1960s, they began developing string theory. String theory is an attempt to describe the world at an even smaller scale than quarks. Today, all elementary particles, including quarks, are described in physics by the Standard Model, according to which the tiniest particles of matter are treated as isolated points. String theory, however, proposes that all particles at a fundamental level are one-dimensional objects, strings, that can vibrate at different frequencies. Those frequencies, in turn, determine which particle with specific properties each string embodies. String theory was initially developed as a theory of everything, intended to resolve the contradictions between the theory of relativity and quantum physics described above. Hopes for creating a quantum theory of gravity and unifying all four fundamental interactions, gravity, electromagnetism, and the weak and strong forces, rest precisely on string theory. Its peculiarity, however, is that to remain viable, it must be formulated not in 3 but in 10 dimensions. To this day, no one has managed to devise a mechanism for properly translating the calculations from that higher dimensional world into our three-dimensional space. During the second half of the 20th century, string theory underwent two revolutions, after which it became clear that it actually splits into several distinct theories, all overseen by M-theory. This overarching framework introduces an additional 11th dimension to carry out rational computations using the most modern mathematical tools. No one knows exactly what the M in M-theory stands for. Some suggest it means membrane or simply brain. Within certain theoretical conjectures, the idea arises that strings need not be one-dimensional at all, but can be higher dimensional objects, those very brains. Moreover, they need not be tiny. Their size is determined by the amount of energy they contain. Minuscule particles, such as quarks, correspond to strings with small energy. If the energy is greater, then the objects represented by the strings can be larger as well. In more recent versions of M-theory, this applies not only to one-dimensional strings, but also to multidimensional brains. Because of energy accumulation, brains can be not merely large in the context of string theory, but gigantic. Hence, the astonishing idea appears that our entire universe is itself a brain. More precisely, a three-brain, since we live in a universe with three macroscopic spatial dimensions. But how, then, can M-theory and universe-sized brains solve the problem of disposing of excess matter and energy after the Big Bang? The solution lies in the fact that the strings forming all particles around us are of two types, open and close. Closed strings are loops, whereas open strings have two ends. What should strings of the latter type do? Where can they put their ends? Calculations show that the only place they can attach is the three-brain of our universe. What is more, those ends cannot be detached. All strings whose vibrations give rise to the elementary particles that carry the fundamental interactions known to us are, according to physicists' calculations, open strings. They can freely glide over the surface of our cosmic brain, but they cannot leave its plane. Therefore, we, who at the most fundamental level is made of these open strings, cannot leave our brain world. In this context, closed strings are exceptional because, having no ends, they attach to nothing and can, therefore, freely leave the brain's plane in the bounds of our universe. According to scientists' assumptions, closed strings generate only the hypothetical particles called gravitons, the carriers of the fundamental gravitational interaction, whose mechanism still remains a mystery. Gravitons are thought to be the only particles capable of moving between different brain universes, as though leaking out of them. This hidden flow provides a key to the universe's outstanding riddles. It was in the form of wandering gravitons that the surplus matter and energy, and likewise antimatter, escaped immediately after the Big Bang, allowing our universe to avoid instant annihilation. The fact that gravitons can travel between brains also explains why gravity is weaker than all the other forces. In reality, it is extremely strong, but across the whole multidimensional multiverse. Only a small fraction of all existing gravitons reaches our three-brain cosmos. This explanation already sounds distinctly fantastic. But what if we propose that in the multidimensional multiverse, brains with the same number of dimensions as our universe lie next to each other, like bizarrely curved ribbons, only a few millimeters apart? That is, the boundary of another universe could be passing right now beneath your smartphone screen. You might even interact with it through the streams of wandering gravitons. Yet you could never touch it or cross its border because the elementary particles that make you up are formed by open strings whose ends are rigidly attached to the fabric of our spacetime. Another intriguing consequence of brains as being twisted ribbons is that between massive objects which, in the brain's plane, are separated by enormous straight-line distances, there may exist an extremely short path through a fold in spacetime. Gravitons can migrate through this loophole, creating yet another channel for hidden, potent gravitational interaction. At this point, armed with string theory and M-theory, we have arrived at truly dizzying notions of how parallel universes might coexist. Yet if one follows all the details closely, the brain concept actually offers a simple explanation for why an event such as the Big Bang could occur at all. According to the hypotheses, we have a higher-order multidimensional multiverse, brains with 3 dimensions like our universe, or even more, and gravitons that can roam freely through this tangle, carrying colossal amounts of matter and energy. In such a system, it is entirely plausible for brains of different universes to touch each other. Because these brains are huge, they also possess enormous energy, and when 2 high-energy entities intersect, an explosive event can occur. Consistent with string theory and quantum mechanics, such an event could give birth to new brain universes. Those brains might either vanish at once through annihilation or, thanks to a random leakage of matter or antimatter in the form of gravitons, preserve their existence. Once again, we must repeat that the multiverse concept in string theory sounds like the stuff of science fiction. Yet, unlike pseudosciences such as astrology or esotericism, the dizzying conjectures of scientists here rest on a physical substrate and a mathematical foundation. That means the existence of multiverses can be checked experimentally. Just not today, and probably not within the next decade. Detecting the brains, closed and open strings described above would require experiments on scales so tiny or so vast, and involving such amounts of energy, that with our current level of technological development, such practical searches are impossible. But everything can change, and far sooner than we might think. In the last century, we merely hypothesized the existence of quanta and gravitational waves. Today, we are already building the first quantum computers and detecting gravitational oscillations with the LIGO Observatory. It is therefore entirely possible that in another 100 years or even sooner, we will see in experiments that parallel universes do indeed exist, and that they are colossal, multidimensional vibrating strings,